Right, sorry for the technical problem. Okay, so I'm continuing with this video. Therefore the second beam, that is PQR, travels an extra distance of xq plus qz than the first beam LMN. And now this is very important to find out what is this extra path distance. So xq plus qz is nothing but the path difference between beams PQR and LMN. So the value of this path difference decides whether the two beams are in phase or they are out of phase, and that would result whether we get a bright spot in diffraction spot pattern or no spot, dark spot in a diffraction pattern. Now let us geometrically calculate the values of xq and qz. Okay, for that we will make some arguments based on geometry. Okay, so if this angle of incidence in is theta, it is possible to show that this angle xmq, angle xmq is also equal to theta. Okay, this is based on some geometry. Similarly, this angle is theta, therefore angle QMZ is also equal to theta. So this angle is also equal to theta. Now let us define sine theta. You have two triangles, triangle XMQ and triangle QMZ. So let us define sine theta in two triangle. Okay, so let me write in triangle XMQ, which is a right angle triangle. Let me see whether I can copy this diagram. So in the right angle triangle in this diagram, okay, let me try to magnify this image. Okay, so in the right angle triangle XQM, Sin theta. Sin theta is opposite by hypotenuse. So sin theta is opposite side, that is x cube, the side opposite to theta, divided by hypotenuse. Hypotenuse is nothing but m cube, that is equal to x cube divided by, this is m cube, this is m cube, this is m cube here, which is nothing but the distance between two planes, which is given the symbol d or dhkl. I will use d. So sin theta is x cube divided by d. Therefore length x cube is equal to d into sin theta. Similarly, if I consider the second triangle, right angle triangle, that is mqz, right angle triangle mqz. Here sin theta is again opposite side, this is theta, so opposite side is qz divided by hypotenuse. Hypotenuse is again mq, that is equal to qz divided by mq is nothing but the distance between the two planes, which is also called as interplanar distance. So you can find out qz is d into sin theta. In my earlier slide, I told you that the path difference between the two beams is x cube plus qz, which now is d into sin theta plus d into sin theta equal to 2d sin theta. Therefore path difference between the two beams depends on the distance between the two planes and also the angle of reflection. Okay, and this path difference should be equal to an integral multiple of wavelength for constructive interference to take place. Okay, you have studied in optics that suppose if you have two waves which are in exactly phase with each other. Okay, so this is the point of origin. Now you can see that both the waves have traveled same distance, so the path difference is 0, which can be written as 0 into lambda. Now I will consider one wave like this, another wave is somewhere here. You can see that the second wave has traveled an extra distance. How much extra distance? Okay, which is equal to one wavelength lambda. So the second wave has traveled an extra distance of lambda compared to one wave, but still you can see that the two waves are in phase with each other. So here the path difference is 1 into lambda, but still they are in phase with each other. So in both the cases the waves are in phase and they should give constructive interference. If I extend this, if the path difference between the two waves is 2 into lambda, then also they are in phase with each other and they undergo constructive interference. So if I generalize this statement, I can say that for constructive interference to take place, the path difference between the two reflected X-ray beams should be an integral multiple of wavelength lambda, that is n lambda. Okay, so if the path difference is 0, that is 0 into lambda, they undergo constructive interference. If the path difference is 1 lambda, then also they are in phase and undergo constructive interference. If the path difference is 2 into lambda, then also they are in phase and undergo constructive interference. If I generalize and say if the path difference is n into lambda, where n is an integer, then they undergo constructive interference. So the path difference 2d sin theta should become equal to n lambda if we want to observe a bright spot in the diffraction pattern. So let us write, therefore what is the condition Therefore, condition to observe maximum reflection, that is a bright spot in diffraction pattern, is n lambda should be equal to 2d sin theta. So 2d sin theta is nothing but the path difference between the two diffracted beams, and when this path difference 2d sin theta exactly matches n into lambda, where lambda is the wavelength of the X-ray that we have used in the experiment. When this condition is satisfied, we observe maximum reflection, that is a bright spot in the diffraction pattern. If this equation is not satisfied, then it means the two diffracted beams are not in phase and therefore they undergo destructive interference, and we therefore observe no spot in the diffraction pattern. And this condition that we have derived here is nothing but called as Bragg's condition, or Bragg's law, or Bragg's equation, okay, which gives a condition for observing a bright spot. Here n, which is an integer, is called as order of reflection or order of diffraction, which is an integer. N is equal to 1, 2, 3 and so on. Lambda is the wavelength of the X-ray that we have used in the experiment. What is d? D is the distance between the two adjacent planes, that is interplanar distance or interplanar spacing. And this theta is not just an simple angle of reflection, it is the that theta which gives a bright spot in the diffraction pattern, and therefore this angle is called as Bragg's angle, that is an angle at which diffracted or reflected X-rays give bright spot. It is not just angle of reflection, it is a very specific angle called as Bragg's angle, which corresponds to a bright spot in the diffraction pattern. This equation, though obtained in a very simple manner by assuming that that X-rays are reflected by crystals, okay, which is a very wrong assumption. But the final equation n lambda is equal to 2d sin theta is able to predict the correct experimental result. That is the reason we adopt Bragg's law, even though it is not technically correct. Okay, so this is a very important derivation even for your examination. I will stop here. In the next video, we will solve some problems on Bragg's equation, and we will write some expressions which gives a relation between the distance between two HKL planes and cell parameters A, B and C. Okay, some useful relations related to Bragg's law. Okay, that would be part of next video, and in the coming videos we will apply the Bragg's law to study the structure of two important solids, crystalline solids, that is structure of sodium chloride and structure of potassium chloride. That would be part of the coming videos. Thank you.